It can be difficult to get a prototype of certain types of materials. For example, gaskets. Gaskets are something that are easily made in production. In prototype quantities, they can definitely be made. But sometimes when a prototype fails, the challenge is understanding whether that was because of the method of prototyping or was it actually a design failure. Prototypes tend to fail at a higher rate than production parts will. Production parts are more durably made, typically, and to a higher fidelity. So sometimes the mistake can be made where you're solving what you think is a design problem, and really it's just a prototyping problem. Understanding which of those two problems it is something that comes with experience, and something that the design engineers are trained on and gain experience on over the years of getting good at this discipline. Where you're using a low-fidelity prototyping method and the prototypes fail. A common mistake is sort of over-engineering the prototype so the prototype is successful, and then you end up with something that uses more material or is larger than it needs to be in production. For example, snap fasteners. Snap fasteners are used to secure parts without screws, so you can snap a circuit board into an enclosure. They're notoriously difficult to work on prototype machines, and they will often fail. So you can build up the wall thickness in the design so that your prototype is successful, but in production you may not need to do that at all. If you're injection molding this part, you wouldn't need to increase the wall thickness. It's just a different strength of materials that comes from an injection molded part than something that's 3D printed. When you're designing a prototype, you are often very concerned with the function of the device and not as much with the regulatory compliance. Anything that's electronic has to meet EMC standards, so that's electromagnetic compliance, ESD standards, which is electrostatic discharge levels. You do not want to fail those tests when your design is done. You need to be in the middle of that design. A common reason for EMC failures is using wire harnesses, or using unshielded wire harnesses, or using wire harnesses that are too long. So you have your circuit board here and you've got a display over here, and when you're assembling that device you need to connect the two and then sandwich it together. Well, something that's maybe easy to prototype and easy to hand assemble a wire assembly, everything looks like it's fine, everything's functioning well, and then you go and put it into an EMC chamber and discover that it's emitting radiation at a level that's higher than meets the required standards. And the cause can be because of that wire harness. If you aren't at the stage where you can change the design, like your design is too locked at this stage, then you have to sort of apply band-aid solutions like ferrite beads to wire assemblies, or electromagnetic shielding, or spraying the inside of an enclosure with the metallic compounds to act as a shield. If you knew that that might be a problem at the beginning, this is what comes with experience, you would know, oh, I actually just need a much shorter cable, or I'm going to use a shielded cable, or I'm going to use a flexible circuit board or a daughter board where those things don't need a cable at all, or I'm going to put ferrite beads on the signal traces right on the printed circuit board rather than wrap the whole cable in a big bulky ferrite bead at the end. Experienced designers and design engineers will know that some of these things are possibilities and will solve those problems at an earlier stage, or at least provide affordances on the circuit boards or in the enclosure to make those problems easier to solve before having to apply these band-aid solutions.